All right, so today's lesson is pretty quick. It's on differentiability and continuity. And we're learning one of the foundation parts of is a function differentiable? And it may be differentiable at certain points, and at other points it may not be differentiable, and that's what we're going to learn about today. This first part, don't worry about it as we go through here, just because it's I need to zoom in on a graphing calculator. Is a little bit challenging to do here, but as we look at the kind of the definition we're following for is it differentiable, the derivative exists for each point in the domain is one thing we got to make sure we keep in mind. The graph must be a smooth line or curve for the derivative to exist. So that's a key thing. It must be a smooth line or a curve for the derivative to exist. In other words, a graph must look like a line if you zoom in really close. And we're going to say local linearity here. Do we have local linearity at a certain point? As they ask us maybe to do it at, is there a point where, does it look like it's a straight line? And if it doesn't, then it's not differentiable. And then there's several different functions out there that are not technically differentiable because at a certain point they fail one of these three things, and I'm getting ready to mention the bottom. The first one is the derivative fails to exist where the function has discontinuity. So we learned back before about our different types of discontinuity. So we have like our hole. So we have that. We have our jump discontinuity. So maybe it's here, and then we open circle and there. So those are two examples of one reason why my function may not be differentiable is because at a certain point, maybe I have some type of discontinuity taking place at that point. The second one is a corner or a cusp. Now, corner is really easy to kind of picture. It would be like your absolute value graph. So maybe it looks like that. That would be our corner. The cusp, we haven't seen that often in prior math classes, but a cusp would be something like this. So it's almost like those little pictures when we were younger trying to draw in art class of birds before we got really good at it. We're down there. There we go. And that's a cup. And then we're going to learn which equation is associated with that graph here in the next couple lessons here. But those are some examples where if I see a corner or a cusp, I am not differentiable at that point. And we think, because again, it goes back to the definition, it must be a smooth line. Well, yeah, we might be a straight line and smooth coming down, but then we hit this corner, and then all of a sudden we're not. And so it kind of takes us away from that. And then the third one would be if we have a vertical tangent. Meaning that maybe there's as I go to look at the slope of a tangent line on different parts of the curve, well, at one certain point, maybe at that point, we actually have a vertical tangent. So with that in mind, we're going to just distort this picture here. So let's say we have this graph, and it went straight up and then like that. And so this would be our example right here, is that I have a vertical tangent. So I am not differentiable at that point there. Again, we in order to be differentiable, we have to be continuous. That's the first part. It's got to be a continuous graph, and then we have to make sure that it's like that there's a smooth line or curve to it. So on the next part here, we're going to identify, okay, where am I not continuous and not differentiable? And remember, some points you may be continuous, but you may not be differentiable. So we're trying to identify the difference here. So first thing that stands out here is that x equals -3. We see that technically there's a hole there, so we would say, since there's a hole there, we would say it's not differentiable. Now, the limit does exist. We can tell the limit is, as x approaches -3 from both sides, is 2. However, it's not differentiable because there is a hole, and also because that hole indicates that it's not continuous. And not continuous. And again, I did, the limit does exist. Those are some sidebar questions they may ask. The next point here, we see x equals -2. We see here that it's continuous. However, it is a cusp in a way. We see a cusp. So not differentiable. Is continuous. All right. Is anything happening here at that y-intercept? No, it's fine. It's differentiable. It's differentiable and continuous. We can see what the limit is. As we approach 0, we see the limit is 2. Next one would be +2, x equals 2. Again, we see another cusp here. So again, not differentiable, even though it is continuous. Okay, even though it is continuous there, it's not differentiable. And then at 4 here, at x equals 4, we would say there's a jump discontinuity. So we are not differentiable. It happens to be not continuous as well. And the follow-up question you'd ask is, hey, does the limit exist? Well, no, there's a jump discontinuity there, so the limit doesn't not exist at x as if x approaches 4 for that function there. So to wrap it up, 2 little questions here to ponder. First, differentiability implies continuity. Is that true or false? Second one is continuity implies differentiability. Well, if you're saying a function is differentiable, if you're saying that it is differentiable, then that means it has to be continuous, because that's one of the things that it stipulates up above. It's got to be a continuous function. So it is true. If you're saying something is differentiable, then that implies that that function is continuous. The next part here, continuity implies differentiability. That is false. We think about our cusp, our corner, those type of things that I illustrated up above in the previous picture. They're continuous. There's continuity going on there. However, they're not differentiable at those points because it's not a smooth line at that point. All right.